Good morning. This is the third and final class of the introductory Lisp course. Today we're going to discuss various kinds of data objects, particularly lists, numbers, and a number of other things like path names, give some examples of opening and closing files, and so on. So starting with a list, what is a list? A list is an ordered, possibly empty collection of objects in the particular list format. And if you look at the way that a list is stored in memory, it is a series of pairs. The first element of the pair is a value, either a value that can be represented in one word of memory or a pointer to a value somewhere else in memory. The second element of the pair is a pointer to the next element of the list. So each one of these pairs, the first element points to a value, the second element points to the next element of the list, until you get to the final element of the list, where the second element points to the symbol nil. And so that is the list ABC. That's how it's laid out in memory. There's no reason that these objects in memory are contiguous. They can be anywhere in the memory, swap space memory that's assigned to the list process. Now let's try the slideshow. For some reason it jumps to free, so there we are. Sort of. A cons is the name given to the data object, which are the various elements of the list. A cons is an object with two components. The first, which is called the car, C-A-R, and then the rest, which is called the cdr, C-D-R, and it's pronounced cdr. Now, these names, just for a little bit of history, came from the names of registers on some early DEC machine, I believe, the PDP-10 or something like that. So, but anyway, the names have stayed with us, and they are car and cdr. And the function cons allocates a cons object. Now, the cons can either have two values, where here we have the symbol A and the number 7, and you end up, which is what is called a dotted pair, or a dotted list, with A the first element and 7 the second element. Notice that this isn't a true list because the final cons does not point to nil in its second element. A true list is given here by cons A nil, and that is the list containing the single element A. And you can build a list by taking conses of conses of conses, with the last cons having a value and then pointing to nil. So this is the list ABC. And we could do this just as well with the function list if we wanted to. So a list, the recursive definition of a list is either the symbol nil, which represents the empty list, or a cons whose cdr is a list. So therefore, a cons whose cdr, that is the second element, is nil, and whose first element is any value, is a list. The list in this case containing B. And since this is a list, the cons whose first element is A and whose second element is this cons, is this list, is also a list, and that's the list AB. Nil, as we said, is the empty list. The symbol nil, the open parentheses, closed parentheses, in other words, representing a list with nothing in it, are equivalent. You can use either one. Nil evaluates to itself. The car of nil is nil, and the cdr of nil is nil. There are a number of other list functions that access elements of the list, and almost all of them, when applied to nil, return nil, as we will see. So a more typical way of creating a list is with the function list, and it just takes any number of elements, any number of arguments, and each of those arguments are bundled up into a list in order. So the list with the symbol Boston, the symbol distance, and the number, presumably speed and time, are variables that have values, and the number that's got by multiplying the value of speed with the value of time. So we end up with the list Boston, the symbol, distance, the symbol, and presumably speed and time multiplied together gave us 1800. When the elements are all the same, you can create a list with make list, and give it, the first argument tells you how long the list is going to be, and the second argument has a keyword argument, initial element, and it is the symbol Denver. So we end up with a list with 3 elements, Denver, Denver, Denver. A more typical initial element, if you don't specify it, is nil, and then you end up with a list with nil, nil, nil. So lists can be simple or have structure. Simple means the elements are themselves simply objects, or structure means that that they contain sublists. There are 2 kinds of lists within Lisp. The association list, which is a list of lists, and the first element, or here we have a list of dotted pairs, and here we have, here's a 2-element list, we can have be a list of 3-element lists, and the first element is called the key, and the remainder is called the value, and there are functions provided for working with association lists. A property list is somewhat simpler. It's just a list, a simple list with a key, value, key, value, key, value. So the keys here are keyword symbols, :A, the keywords :A, :B, and :C, and the values are 1, 2, and 3. And property lists are used all throughout Lisp. Every symbol has an associated property list which you can store values on. You have to be careful that the property list of a symbol is used by the system, so you should only add values to the property list. You shouldn't replace the property list of a symbol. And it's another way of associating keys and values. So lists are very useful for data structure. They can be of any size, up until you run out of computer memory. In other languages, you must typically write your own Lisp primitives, that is functions, but in Lisp there are a lot of functions already provided, and as I said, there are many built-in functions, and we'll see quite a few of them in the next slides. So here are a whole series of list operations. The first takes the first element, that is the index 0 element. It's a slight mismatch between the name of this function and the way lists are indexed. Everything in Lisp is 0-based indexing, but still, in order to access the first element, you still use the function first. First of nil is nil. As I said earlier, almost any list function applied to nil returns nil. The rest function takes the sublist after removing the first element. So the value of first is a element of the list, or nil if the list is nil. The value of rest is itself a list. Rest of nil is, of course, nil. Second gets you the second element of the list, and there's also third, fourth, fifth, sixth through 10th, and we run out at 10th. And notice that second is equivalent to first of rest of ABC. There's third, second of nil is nil, third of nil is nil. There is a function nth, which takes any element of the list by index. And so the equivalent of first is nth 0. The index comes first, then the list. Nth 0, ABC, is the first element, or A. Nth 2 is the third element. Index A is index 0, B is index 1, C is index 2. Notice that if you specify an index which is bigger than the length of the list, or equal to or bigger than the length of the list, then you get nil back. You don't get an error. There's nothing wrong with trying to access any index of a list. If the index is too big, you just get nil back. There's no way for you to tell just from this result whether the list was long enough and the value was nil, or whether you've gone over the end of the list and so it's returning nil for that reason. You would have to look at the length of the list and compare it with the index you've provided. There's the length function, and it gives you the length of the list. And here we have a list containing 4 symbols, and its length is 4. The length of nil is always 0. Let me show a few of these there we go, in our list, just to, so we're going to set our list to, let's just do 1, 2, 3, 4, 5. So it's a list of 5 elements, 1 through 5. And so first list is 1, nth 0 list also 1, nth 10 list is nil, and 10th list, which is actually equivalent to nth 9, also nil. Let me do another list here, and I'm just going to create one. So let me just show you. Should hit a parenthesis there. There we go. So 1, 1, 2, 1, 2, 3, 4, 5, and 6, 7, 8. Oh, let's do one more. Nil, 9. There we go. So what should the length of that be? How many elements are there? The first element is the number 1. The second element is a list. Even though it has 2 elements, this only counts as 1 element of the list we've created. So 1, 2, 3, 4, 5, 6, 7. We should get 7. And we do. So what is the nth 5 of, sorry, I have to copy this. I didn't make it the value of a variable. And you notice that it's nil because the index 5th, that is the 6th element, is nil. Just from that result, I mean, we couldn't tell. We also do 10 of the same thing. And sorry, I went one parenthesis too many. We do 10, the index 10 element, and we get nil. There's no way to know whether the list was returning nil because that was the element or returning nil because we'd exceeded the end. You have to look at the length in order to determine that. So let's go back to the slides. And there are all sorts of functions that look for an element in a list, and we're going to go through a number of them here. There are going to be more than you see here. One of them is member. Member takes as its first element an object. In this case, we're giving it the symbol Dallas. And as its second argument, a list. Here's a list of city names: Boston, San Francisco, and Portland. And then, like many of these functions. It also takes additional keyword arguments where you can specify what you mean by being a member, by specifying a test function, and you can, there are various other arguments. We're going to mention a couple of them. So Dallas is not in this list, so it returns nil. But Boston is in the list, and what member returns is the list starting at the element that you've found. So Boston is the first element of the list, so it returns the entire list. Portland is the third element of the list, so it returns the list containing just the city Portland. And remember, anything other than nil is true. If member finds an element, an item in the list, it returns a list starting from that element, and therefore it is returning a non-nil value. It's not returning the empty list because the list, this element is there. And so anything other than nil is true. It is, by the way, we'll find as it's written, the first element, if an element was repeated, it would return the first one, and there's a from-end argument which would allow you to start looking backwards. And let me just demonstrate that. So let's make a list. Well, I actually have one. Let's see what it looks like. Let's make a new one. Quote, 1, 2, 3, 4, 3, 2. Okay, so member 2 list, and you see it starts the sublist with the first occurrence of 2. Now, I think this works. 2 list from end T. Let's try this. It doesn't like from end. So I guess a number of these sequence functions have a from end argument. Let's actually look at what the arguments to this are, since I seem to have forgotten them. 2 documentation pages. Yes, because members both a type and a function. And this one. And let's go back. So here's member, member if not. Member takes item list, and it just has the keyword arguments, key, test, and test not. So we'll demonstrate from end with a different function. Their lists can be considered sets, and there are set operations, union, intersection, set difference. Union takes any number of lists as arguments and returns a list that contains all the elements of all the argument lists, removing duplicates. So you notice that 2 and 3 appear in both of the lists, but the union, they each appear just once. Intersection takes the elements which are in both lists, and set difference takes 2 arguments, and the first is a list and the second is a list, and the result is the list that where all the elements in the second list that appear in the first list are removed. Notice that in this case the order is changed. You are never guaranteed the order of the result of union, intersection, or set difference. The order can be anything. All you're guaranteed is you get the right collection of elements. And actually, these are, I always forget certain elements of these things, and you just have to test them to know what's going on. Let's just try a... So what happens, I'm curious to know, if, so we're doing the union, and here we're going, and the second one we're going to have 1, 2. And it's only guaranteeing that the, you notice we ended up with 3, 3, 1, 2. And every element that is in one or the other of the lists appears here. One of them actually appears twice, the 2 3s, even though there were 2 2s as well in the first in the first list, and there was another one in the second list. Only 1 2 appears in the final. And let's just look quickly at the documentation of union. List 1, list 2, bunch of keyword arguments, and let's see what it says. For all possible ordered pairs, considering one element is used to determine if there duplication between only one of the duplicate instances will be in, if either list has duplicate entries, the redundant entries might or might not appear in the result. And that is precisely what happened here. We had a redundant entry of 3 appeared twice. Both of them appeared in the result. 2 appeared twice, and again in the other list, but 2 only appeared once. And this is, it is important that you look at the documentation in these cases, and when you see this statements like duplicate entries, redundant entries might or might not, that means that you really can't tell. You're going to get one or the other, and if it's important to you, after a result of union, you have to do a remove duplicates or something to get the redundant entries out of there. Now, car and coulda are the 2 functions that we've already mentioned. Car is equivalent to first, and coulda is equivalent to rest. It's actually recommended that you use first and rest because they're easier to understand, but lots of old-time Lispers use car and coulda, and you hear those terms all the time. And there are additional functions where you can have the car of the coulda of foo. The coulda of foo is the list 2 3. The car of that is 2, so you get 2. And this can also be written as CADR. And that's pronounced, not that anybody pronounces it, cadder, CADR. And you can have up to 4 letters in here that are A or D, any combination of A's and D's. And the way you read this is backwards. You first perform the coulda, and then you perform the car. This is the exact equivalent of that. You can have up to 4 combinations of A's and D's. Using these type functions is even less recommended than using car or coulda, but you may occasionally see them in Lisp code. Now, copying a list, there's a function copy list, and it takes a list and it creates a new list with the same elements, and the 2 lists, here we have A equal to the first list, B equal to the copy list. They are not EQ, they're not EQL, but they are EQUAL. EQUAL, when it compares lists, sees whether they have equal elements, and if they do, it returns T. These 2 lists have equal elements, but they are not the same list. And you'll see why that's important in a minute. So let's see what copy list is doing. So here we have the variable x. Its value is the list ABC. Now remember what a list looks like in memory. There's a pointer to the symbol A and a pointer to the next element of the list. Pointer to the symbol B, pointer to the next element of the list, pointer to the symbol C, and the coulda of the final element of the list is nil. Similarly, Y is a separate list, separately in memory. That's why these 2 things are not EQ, but pointing to the same 3 elements, A, B, and C. When consider copy list of X, where X is the symbol A, the list containing the symbol B, and the symbol C. Y is the copy list of X. So again, we have these two separate lists in memory, but pointing to the same elements, to A, to the list containing B, and to C. Now, we'll get back to this example in a minute, because it's important that we, when we start modifying lists, you can see that when we modify the first element of Y, it makes it a different thing than the first element of X. But when we modify the contents of the list, which is the second element, both X and Y will see that modification. We'll see that in a minute. The last function returns the last cons of a list, not the last element. It returns the list containing the last element. Also has a count optional argument, and in that case it returns more elements starting from the end. So we have the list, 1, 2, 3, 4. Last applied to it is the list containing the last element, the list containing 4. Last of A with the optional argument 2 is the last list containing the last 2 elements of the list, 3 and 4. The car of that, it's a list. The car is the first element, is the element 3. You have a bunch of lists, and the function append simply runs all the lists together. All the argument lists except the last are copied. The last element list, the last list is simply used. And so we set QA to be 1, 2, 3, 4. We set QB to be 5, 6. And we set QC to be 7. And D appends all of those things together. And so let me go and show that, and I'll show you. So we set QA to be 1, 2, 3. I don't know. I'm going to do the same thing. Can't remember what it was. E to be 4, 5. And set QC to be the list 7. And we set QD to be append A, B, C. Now, the function setF changes and a place. We're going to go into setF later, but what are we doing? First of A to 22. And what did I do wrong? Okay, let's do that again. Left out a parenthesis. Actually, put in type setF twice for some reason. We'll just get rid of that second one. And that thing, and there we go. So now let's look at A. A is 2223, but D is unchanged. Now let's try that with C. Oh, sorry, I had an extra parenthesis. There we go. So C is now 99. And D is also changed. It didn't copy C. The final argument to append is not copied. So it's simply sharing the memory with D, shares memory with C. So when you modify C, you modify D. When you modify the bit of D that came from C, and what is that? First, second, third, fourth, fifth, sixth. D to 0. D has a 0. C is modified to 0. It's just important to remember while you're working, manipulating lists, if you're going to continue using things and if you're modifying things, it's important to remember what bits are shared and what bits are not. And we'll see another example of this shortly. So there's a pen, copies all args except the last, as I showed. There's a function called nconc, C-O-N-C, which is a destructive version of append. There are a lot of Lisp functions which are called destructive, meaning that they modify their arguments, and so the arguments after the function's been called may or may not be different from what they were before. And so here we have the list 1, 2, 3 is the value of A, 4, 5, 6 is the value of B, and C is nconc A and B. It's 1, 2, 3, 4, 5, 6. And B is unchanged, but notice that A is also changed to 1, 2, 3, 4, 5, 6. Now, an important thing about destructive functions is that even though you might look at them and think, oh, after I do an nconc of AB, I can depend on A being the union of the two, the concatenation of the two lists. That's not true. You cannot depend on how a destructive function will actually modify its arguments. It may do something different from what you expect. Destructive means that the argument values after the function has returned are no longer meaningful, and you should not, again, use them. So the advantage of this is that if you don't really care about the values of A and B, you're just using them to construct C, then destructive functions like nconc are faster and more memory efficient than non-destructive functions like append, which goes around copying a bunch of arguments. So you use destructive functions where you no longer care about the arguments. You use non-destructive functions when you do care that the arguments maintain their values. By the way, almost most or many destructive functions start with the letter N, and usually are the letter N put before the non-destructive function. So when you see an N, you think this might be a destructive function, but there's some, like the function nth, that we've already been introduced to, which are not destructive, and they're called that because that corresponds to an English word. So, but when you see an N, particularly when it's not making sense, like nconc, there's no English reason why the N is there. You think, that might be a destructive function. There's a function replaca, and there's a whole function, but replaca is short for replace the car, changes the first element of x. So replaca xy should be parentheses around that, changes the first element to the second argument. So we have A being list 1, 2, 3. Replaca A4 changes the first element to A. Replac D replaces the coulda, replace coulda. And Lisp is always making words and then throwing out a bunch of letters. So if you sort of look at that, you can see replace coulda, or not, but anyway, that's the function. I myself tend not to use these somewhat obscurely named Lisp functions, and here is the equivalent, and I just find that much easier to read. I know what this is doing, setf restx to y. I know what that's doing, and replaca or replacd, I often have to go and look at the documentation to remind myself. There are functions push and pop. They're actually macros, and you can push things onto a list and pop things off a list. And so here's the list mynetwork, set as the value of mynetwork. It's got 3 symbols, power, GND, and input. And I can push the symbol CLK1 onto it. And at this point, I've modified the value of that variable. I can pop the first element of the list off. And again, I've modified the value. So push and pop are convenient tools for generally if you have something like a list of things that have to be done, you push new tasks on, and as you do tasks, you pop them off. And so they're actually convenient macros for list manipulation. Now, here's the setf function, macro actually, which I've already used. You're already familiar with setq, but setq takes a symbol as its first argument. The symbol is naming a variable, and it sets the value of the variable. Setf takes any form that, if executed, would access a value. A symbol accesses the value of the symbol viewed as a variable, but other things like first, as I demonstrated, car, coulder, all of those things also access values in a list, and therefore setf you take that form, in this case second of A, and you're saying change the value which is accessed by the second of A and change that value to magenta. So the value is called a generalized reference. Second of A is a generalized reference to a location in the list A. The accessor is called by itself. Second of A called by itself would retrieve the second element of the list A. Setf of the generalized reference stores the replacement value. So after you've done this, the value of A will be red, magenta, blue. We've already mentioned push, but here's push again. Push also works not only on lists, but on generalized references to list. So here we have list 1 and list 2, 3. So this is the two-element list containing 1 and the list 2, 3 as the two elements. And we can push the symbol X onto A, and we get X1, 2, 3. But we can also push the number 9 onto the third of A. The third is now this list, and so the result of that is that A is now still a three-element list, but its third element has now been modified by having 9 pushed on the front. Pop also works for general, so we could pop the third of A. We would get 9, and it would remove it from that list. Push new is a function, actually again a macro, and it adds an element to a list if it's not already there. So here, the first time we do push new of the second of A, which is a sublist 2, 3, A gets modified, so its second element is now 9, 2, 3. But if we do it again, it would not make any change because 9 is already a value in the list at that location. So now let's go back to copies, and I will demonstrate the shared memory issue again. Here we're setting X to a three-element list. The first element is itself a list. The second and third elements are symbols. And we set Y to copy list. So both X and Y point to this list B, and then point to the symbols A and the symbols C. So there we go, and we do copy list, so there's X and Y. If we change the second value of X, that is the symbol A, to K, the symbol K, we change the list X, but the list Y is unchanged. If we change the element in the list, which is the first element of X and also the first element of Y, from the symbol B to the symbol M, it gets changed in both lists because both lists share the memory which is storing this first element, which is itself a list. They share that list in common. Any modification to that list will be seen by both of them. And here is just an illustration of what we've just done. In memory, now we're pointing to this same list here, but now the car of this element of this, the first cons of the list, the first element, the car, points to M rather than B, which is what it pointed to before. Now, printing lists, there are two variables, print level and print length, that control the printing depth and length. So the value of these variables can be a number, or it can be the symbol nil, meaning unrestricted. In Allegro CL, but not in standard Lisp, there are two additional variables. These are in the Common Lisp package. They have the same name, but are in different packages. The package is the top level package, called print level, again, and print length. And they control top-level printing. Top-level printing is what happens when you are evaluating something in the listener and it prints a return value. The function pprint, standing for pretty print, always prints a whole list, and it is recommended that you not set the top-level variables, that is TPL print level and TPL print length, to nil. By the way, typically when you're reading a variable that has stars on the end, you just give the name and don't bother with the stars. But since you can see the slides, the stars there, and I just refer to these as print level and print length. So let's see what this is doing. We're setting the list, the value of the variable LIS, to be the list that contains the symbol A, and then as its second element, this rather complicated list that each has two elements. The second element is itself a two-element list. Whose second element is itself a two-element list. Whose second element is just a one-element list. And so that's A is the first element. The second element is this list. And then 2, 3, 4, 5, all the way up to 11. When we do that, we evaluate that. The return value, when we do that, is going to be printed like this, because in the oh, that's actually wrong. There should be another parenthesis there. Sorry. There should be an opening parenthesis so that the first element is actually this first element is the list starting at A. The slide's incorrect there, because see what the return value is. It's a list containing this complicated list, then 2, 3, 4. Now the initial value of TPL print level, print length is 10, and print level is 5, I think. We can look in a second. Anyway, so it's only printing 10 elements. The first one is this list, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then to show you that there are additional elements, it prints ... It's only printing 5 levels. So when we get down, so A, and then the sublist, and a sublist of that, and a sublist of that, and then it gives up and replaces the additional levels with a hash mark. So when you see a hash mark or a ... that indicates that the printer has not printed everything because it is run into the restriction of the print length of the print level. Now, if we use print, it prints the list first using the Common Lisp variables, print level and print length, both of which are initially nil, meaning no restriction, and then it returns the thing it printed, and so here is controlled by top-level printing, and you can see the difference here. The entire list, all the depths, and all the elements are printed by the print function, but then it's abbreviated when printed by the top-level evaluator. And the function pprint, standing for pretty print, always prints the full contents of the list. Now, the reason that we suggest that you not set the top level, print level, and print length to nil is that every once in a while you happen to access a list, typically an internal list, that is very, very long, has hundreds or thousands of elements. And if for some reason that comes up in an evaluation, so it would be printed out, you would just get a very great deal of stuff printed to your screen, which you're not interested in. So you have the top-level variables set to reasonable values, 10 and 5, and then if you want to look at the complete value of a list, you can use pprint or print or something in order to do it, but you don't accidentally get huge lists printed to the top level without you yourself specifying that something should be done. Okay, that's what we're going to say about lists so far, and now we're just going to go on and look at numbers represented in Common Lisp. And the thing about Common Lisp is that it has many different kinds of numbers, number representations. There are integers, and integers can either be fixed nums, which are reasonably small integers, we'll see how small shortly, or big nums, which are integers of any size. And when you're doing manipulations, adding, multiplying, etc., the system automatically shifts from the mode of manipulating fixed nums to big nums. The thing you have to remember is fixed nums are computationally and from a space point of view very efficient. Big nums are computationally and from a space point of view reasonably inefficient. That is, time-consuming to work with them, and space inefficient. They use a lot of space. So you always want to be careful that you're only using big nums when you really need to use them. There are ratios, which are a ratio of two integers. There are floating point numbers, and there are complex numbers. And so all of these types are supported within Lisp, and here is the type hierarchy. Number has two subtypes, complex numbers and real numbers. Real numbers can be rationals or floats. Rational can be a ratio or an integer. An integer can be a fixed num or a big num. And there's also a particular kind of fixed num called a bit. If something is of type bit, it is either 0 or 1. That is, it can be represented by 1 bit in the computer, 1 light, which is either on or off. Fixed nums can be represented in 1 word in a computer, and everything else is represented by a more space in the computer. In the floats, there are 4 types of floats defined: short float, single float, long float, and double float. But in Allegro Common Lisp, their short float and single float are the same. A floating point number represented by 1 word in memory, 32 bits on a 32-bit machine, and 64 bits on a 64-bit machine when you're running a 64-bit Lisp. Long float and double float are the same, represented in 2 words in memory. So 64 bits on a 32-bit machine, or 128 bits on a 64-bit machine. The short floats and single floats, long floats and double floats are represented in Lisp the same way they're done in other programming languages like C, etc. And if you know how these things are represented, there's a single bit used for the sign, and for a 32-bit, there's a single floating point number, 1 bit for the sign, 8 bits for the exponent, and then 23 bits for the value, except there's an implied 24th bit. Since the first bit of the value is always 1, it's not represented. So the value is represented by 24 bits, the exponent by 8 bits, one of which is the sign, and the sign by 1 bit. Now, 24 bits binary is equivalent to 8 bits decimal. So a single float on a 32-bit machine is accurate to 7 or 8 decimal places. And it's always important to remember floating point arithmetic is inherently inaccurate. And you just have to manage the inaccuracies so that they don't get out of hand. Where did we go? That was so fixed nums, the most positive fixed num and the most negative fixed num are two values that bound the range of fixed nums, and fixed nums efficiently map into the underlying hardware's integer operations. And let's just look at what those values are. Most positive, I wish I could spell, fixed num, and I was supposed to complete faster than that. That's control period will complete symbol names. So, and most negative fixed num. Now, one thing to notice, the size of the most positive fixed num is, what are we doing here? So that's thousands, millions, this is on 32-bit machine. It's 536,870,911. The size of the most negative fixed num is 536,870,912. You notice that they're unbalanced. That's because they're only an even number of fixed num representations available, and we need one of them for 0, so we can't have the same number positive as negative because we've used one fixed num. 0 is a fixed num. Let's just expt to the function expt takes an argument, raises it to a power, let's see, 30, what's 30, just out of curiosity. That seems too high. expt 229. Yeah, there we go. So basically, we are representing fixed nums with 29 bits. We need 1 bit for the sign and 2 bits. Well, actually, the first 3 bits are used as a tag, saying this is a positive fixed num or 0, or this is a negative fixed num. And then the remaining 29 bits of our 32-bit word are the value. So basically, we get 29 bits of value. So most positive fixed num, most negative fixed num. There's a function fixed num p, which tells you whether its value is a fixed num, and most positive fixed num is a fixed num, but fixed num p 1 plus most positive fixed num is not, unsurprisingly. So that's a big num. That's why it's called most positive fixed num. That's the type hierarchy, and this is what I just did. The function type p, we'll get to this a little bit later, says, is this value of that type, and most positive fixed num plus 1 is of type big num 1, and all the way up to 500 million plus would be a fixed num. Now, Arithmetic operations are generic. That means that you can take any arithmetic function and apply it to any type of value, an integer, a ratio, a real, a complex, and it will do the right thing. And it will start out by taking its arguments and what's called canonicalizing them, or changing their types in order to be the type appropriate with the other arguments and with the function that you're calling. So that if you're calling sine or cosine, it's going to take integer arguments and convert them to floating point numbers, because the result of sine and cosine is always a floating point number. But if you're doing plus and all the arguments are integers, the result will be an integer. Now, here are some things that go on automatically. Rational canonicalization means that if you have a ratio where you can divide out, so for the ratio of 4 and 2, it's actually going to change it to the integer 2. If it's the ratio 6 and 2, 6 and 4, it's going to change it to the ratio 3/2. Floating point contagion says that if there are a mix of integers and floating point single floats and double floats, it will convert everything to a double float. If there are integers and single floats, it will convert everything to a single float. And complex contagion says that if there's a complex number, all the other arguments will be turned to complex numbers, and complex canonicalization means that if you have a complex number with a 0 imaginary part, it will be changed to a real number. So let me just quickly show what all of those things mean. So if we do divide 3, 2, we get the ratio, but if we do divide 6, 4, we again get the ratio 3, 2, not 6, 4, because it is canonicalized it by taking out the common factors. Floating point, so we'll do floating point contagion. If we do plus 1, 2, we get an integer. If we do plus 1, 0.666, 7, we get a floating point number as a result. And just notice that little 0, 1 that appeared there. As I said, floating point arithmetic is not exact, and you tend to get errors or variations from the, quote, true, end quote, value appearing. And because Lisp prints numbers out completely, you see these variations, and sometimes people find them disturbing. But the reason I put true in quotation marks when I said that is that it's actually wrong to think of floating point numbers as true values. Floating point numbers are the best representation of a whole cloud of real numbers that surround the representable numbers. These numbers are representable only up to 8 spaces, 1, 6, 6, 6, 6, that's 5, 7, 0, 1. Here we are at the 8th digit. The 8th digit is inaccurate and is always going to be inaccurate. Oh yes, complex canonicalization is, so here's the complex number 1.0, 2.0, and it prints itself. But if we did 1, 0, it would convert itself to the integer 1, because the imaginary part is 0. So here are floating point numbers. There is a variable called the read default float format. Its initial value is single float, and so when there's an E exponent marker, or when you have a long thing with a decimal point and then values after the decimal point, it will read those two numbers, according to the value of the variable, read default float format, and therefore read them as single floats. If you use S meaning short, F meaning single, D meaning double, or L meaning long, and yes, F does mean single. S and F, short and single, begin with the same letters, so we have to use different letters to represent them as the exponent marker. Then you'll get what you specify, a single float for S or F, because in Allegro Common Lisp and in most programming languages, short floats and single floats are the same thing. A double float for D or L. Most people just use F or D or S. S and F people use pretty interchangeably. Very few people use L unless the implementation actually supports long floats different from double floats. Just as there was most positive fixed num, there are most positive or negative single float, double float, long float, least positive or negative single float, double float, long float. Let's just look at those values quickly. So most positive double float is some value raised times 10 to the 308. Most positive single float is 10 to the 38. The least positive double float is 5. Notice that's a larger number, but there's also a normalized. Normalized is a particular kind. Let's see. And so that's a little bit more corresponding to the most positive double float. A normalized, I'm not really going to go into it, but a unnormalized number is one that doesn't have that leading bit, assumed leading bit, and therefore gets less and less accuracy, but does give you a few more ability to represent smaller and smaller numbers. Now the function float takes a real number and makes it a floating point number. The functions truncate, round, floor, and ceiling map to integers. So we're going to show that on the next slide, but I'll just do it quickly. Float 1 changes it to a single float, and if you have an additional argument, which is here we have a double float number. The only thing we're using the second argument for is to tell what to convert it to. It could be any double float number. And it would still convert it. It's just looking at that second value and saying, oh, that's a double float. That's what he wants me to convert it to. And so that's just what we did. Float 1 returns 1.0. Float 2/3 returns the single float, 6666667. Float 2/3 with the second argument, 1.0 D0. Actually, a whole string of sixes here, much longer. And then here is a very important one to notice. When you float the result, the single float, 6666667, and make it a double float, that's what this is saying, take this number, make it a double float, you get nonsense bits added on. You don't get something that looks nice. When you convert a single float to a double float, it's not going to look like what you expect. That's more about nothing to do with Lisp. This would happen in any programming language. It's just floating point numbers are inherently inaccurate, and you just have to manage the inaccuracy to make it work for you. That's a general programming concept nothing to do with Lisp. You see it in Lisp because Lisp is very good about printing out complete values. If we just printed out the first, 6666666 and didn't print out after this point, it would look like 6666667. But because Lisp prints out the entire value, you see the inaccuracy which has been introduced. Okay, floor, ceiling, truncate, round. Floor takes a floating point number or a ratio and truncates it towards negative infinity. In other words, it takes the largest integer, which is smaller than or equal to the value. Ceiling truncates towards positive infinity. It takes the smallest integer, which is greater than or equal to the value. Truncates towards 0. In other words, it takes the floor of positive numbers and the ceiling of negative numbers. And round truncates to the nearest integer. If so, round of 0.9 is 1.0, is 1, and round of 0.5 goes to the even number, which is 0, etc. And here are some examples. Floor of 2.5 is 2, minus 2.5 is minus 3, ceiling up to 3, up to minus 2, truncate 2 and minus 2, round goes to 2 for less than 2.5, to 3 for bigger than 2.5, and to the nearest even number when it's just 0.5. So round of 2.5 is 2, round of 1.5 is 2. Floor and all these other functions take a second argument, which is divided into the first argument in order, and then the result is actually truncated. The second argument defaults to 1, which is why it makes it, we could put it in here as 1, but if it's 1, divide that into anything, you just get the anything. And all these things return, we only show one return value, but they in fact return two values, the integer part and the remainder. So floor of 5, 2, you divide 5 by 2, you get 5 halves, or 2.5. It would be the ratio, 5 halves. So the floor of it is 2, and the excess is 1/2. It's 1 of divided by that value. The floor, and this value, by the way, is in the same type as the first argument. So in the first argument, it's a real. We get a real as the second return value. First return value is always an integer. Second return value could be different. The thing about ratios, there's no loss of precision, and so there are some cases, there's a missing open parenthesis here, I noticed. But when you do things with floating point numbers, even though 2.5 looks accurate, you are going to get loss of precision. Complex numbers, complex 0, 1 is imaginary part 1, canonicalizes to a real number if the imaginary part 0. There are functions real part and imag part in order to give the same number of letters. The complements of any complex number of any type could be a real number, and complex numbers will appear in, so if we do the square root of 2, we get, of course, 1.414 ... If we do the square root of -2, we get a complex result. So there are a whole bunch of predefined mathematical functions. EXPT takes 2 arguments and raises the first argument to the power of the second argument. Both of these can be real numbers, by the way. They can be complex. The logarithm, x, and n takes this is the logarithm of x to base n. Again, can both actually be any real numbers. Log x is, in other words, without the second argument, is using base e, the natural logarithm. exp is the e raised to a power, the natural exponential function. We got square root, which gives you the real square root or the complex square root of a number, and I square root, which gives you the integer square root of something. And let me just show you what that means. So I square root of 2 is going to be 1, I think, yep. And I square root of 4 is going to be 2. So it's just giving you the floor. I'm not actually sure what I square root of minus 4 does. Ooh, it didn't like it, right, because there is no integer square root of minus 4. It's an imaginary number. That's actually what I expected to happen, but couldn't remember. And just to remind you, whenever you want to know, what does this function do with some odd argument, some curious argument like a negative number, the easiest thing to do is try it out, go look at the documentation, see what it says. There are a whole bunch of trig functions. There's sine, cosine, tangent, and there's arcsine, arccosine, arctangent, and a whole bunch more which we're not even going to mention, like the hyperbolic arccosine and so on. A couple of useful macros are incf and decf, which adds 1 to its argument or subtracts 1, in the case of decf, to its argument. And so this is equivalent to set f a or set q a to a plus 1. incf can take a second optional argument, which defaults to 1, which says actually add this amount to the argument. So incf and decf are macros, as we said, as are push and pop, and indeed setf. Macro expand, the function macro expand transforms the macro call into the underlying code. So here we have set q, we're setting the variable a to 1. What does incf do? Well, you just do macro expand of that form, the list, which is the call. Remember to put a quotation mark at the beginning so it doesn't just evaluate the form. Macro expands the function, evaluates its arguments, and this is what the macro expansion looked like. It's set q a to a plus 1. And you can macro expand anything. Let's, I think list is still a list, right? Yes. So macro expand, which I should spell right, push 10 list. And again, set q list to the columns of 10 and list. And just out of curiosity, what does push new do? Push new, remember, adds it. So there's a function adjoin, and just test whether item is the same as the existing element of the list. If it's not, adjoin adds it to the list as if by cons and returns the resulting list. Otherwise, nothing is added to the list and the original list is returned. So I'd even forgotten there was a function called adjoin, but you see it, it appeared out of push new. What I'm doing, by the way, when I click on a symbol and then I hit F1, that brings up the documentation page. Okay, that's all we're going to say about numbers. Now we're going to talk about some other data structures. We've already dealt with lists. Remember, every object within list has a type. Every object is typed. Variables are not typed. Variables the value can be any object, but whatever object it is, it has a type. You can use the function type of applied to any object, and it will tell you what type it is. And you can use the function type P and apply it to an object, and it will, and its arguments are an object and a type, and it will tell you whether the object is of that type or not. And let me just show you something quickly. So we have type of has a hyphen. 1 is fixed num. So type P, 1 fixed num, obviously is going to return true. But also, this would work with any one's also a number, and it's also a real. So way back, I showed you a slide with the hierarchy of numbers, and you could look at that in any of the types. If you look at a fixed num, any of the above types, type P will return true for. But type of will give you the most specific type. So type of 1 is going to be fixed num. So we've already run into lists, which are chains of concells. Lisp also supports arrays, hash tables, class classes, many of which you can define yourself, and structures, some of which are predefined, but is another thing where you define things yourself. We're not, in this course, going to go into class classes, structures, or hash tables. We're mostly going to be looking at lists and arrays, but they are also very useful. Hash tables trade speed of access for space. They take up a lot of space in memory, but you can access things really quickly. And class classes, you can define things, and structures, you can define things that are specific to your needs. And they're all very useful, and the intermediate course discusses them in much more detail. We just don't really have time in this course to discuss those. So arrays must allow at least 8 dimensions. Look at the variable array rank limit. At least 1,024 elements per dimension in Allegro Common Lisp, but in most Lisp implementations, those values are much larger. Arrays can either store general objects or be of a more specialized objects, arrays of characters, arrays of single floats or double floats, arrays of fixed nums are typical specialized arrays. The thing about specialized arrays is that they can be manipulated much more efficiently if you provide correct declarations to the compiler. So here's an example. Arrays are created with make array. You specify the dimensions. You can optionally specify initial elements and indeed initial contents and a number and element type, various other arguments. But here's the array. It's got, it represents its values as 2 lists. The first row, if you take this as row column, the first row and the second row. The function aref, A-R-E-F, meaning array reference in the usual Lisp, let's throw out lots of letters style. So aref takes an array as an argument, and then the index for each dimension. Indexes are 0-based. Unsurprisingly, that's this element here, 0, 0, this element here, the first row, the first column, the value is nil. You can use setf to set the value, and here we're setting it to the symbol B, and now here's what the array looks like with B there. Vectors are one-dimensional arrays, and you can create them either with make array, specifying just a number as a dimension rather than a list. This first argument be a list or a positive integer. Actually, it can be 0 too. This could also be the list with the single element 4. That's equivalent. Initial element 0. So we have a vector. Notice that arrays are represented as hash, 2, well, the number of dimensions, and then A meaning array. Vectors are just represented hash, open parenthesis. And we evaluate it. We get that. We can set, so here, vector, we can use also the function vector. It's like the function list. It creates a vector with elements and length determined by the additional arguments. So here we have the string containing the single character A, the symbol B, and the number 5. Vectors like lists can contain any elements unless you specify them to be of a particular type. And again, we access vector elements with aref, and also svref is a specialized optimized function. Aref has to look at its argument and say, okay, it's an array, so how many dimensions does it have, and how many arguments do I have, etc. So it's got to do a little bit of extra work at the beginning until it figures out it's dealing with a vector. But svref is knows that its argument is a vector and it's only going to have one dimension or index argument. So it's a little bit more efficient. Strings are just vectors of characters and can be accessed with the specialized char function. Char is the same as aref or svref, and it just says get this index element. And you can do setf on char or on aref if you wanted. And we change the last character, that is index 2 character, to Z. There we go. There are a whole bunch of string functions, and so you can say string equal will be true if the strings have the same length and the same contents, with the string hyphen E2UAL is case insensitive, so foo and capital F foo are considered the same. String equal sign is case sensitive, so these two strings are not the same. Less p and greater p. Less p says is the string starting with letters earlier in the alphabet, or greater p is it later in the alphabet. And then there's the question of where do capital letters go in, there's also string less than, and see if we talk about capital letters, and very annoying today. Let me go look at capital letters and numbers just to, so A, B, C, by the way, with set Q, you can have as many pairs as you like, and it will just set all the values. 1, B, C. Now let's do some testing here. So string less than S1, S2, nil, string less than S2, S1, and string less than or any of these string comparison functions returns the first character where it makes a difference. So this tells us that capital letters go before lowercase letters, and let's try string less than S1, S3. Numbers go before letters. I can never remember those things, so when I need it, I actually just go test things. That's the way, quickest way. There's an awful lot to remember. It's much easier not to clutter up your brain, but just go test things when you need to know. And so string trim. So we have a string and space, space, FIVE, space, TEN, space, space, space. String trim says remove any spaces from the beginning up to the first non-space and from the end back to the last non-space. Gives us 510, but doesn't remove the space in the middle. String trim space and $sign. Notice the $sign disappears, but not the one in the middle. In other words, it stops trimming and then works from the end and goes back, but it leaves the things in the middle unchanged. String upcase, string capitalized, string can be applied to a symbol and it returns the name of the symbol. Since we're in an uppercase list, the symbol 5 has name, all capital letters. And alphabetizing strings, yes. So I showed you some of that. String greater than, less than or equal to. Is string less than this, less than that? And the answer is no, because I is less than A. Is string this greater than string? Yes. And it starts being greater in the second index, that is the third character. Shorter strings are less than longer strings, even if they're the same up through the length. Again, you don't remember these things. When you need to know them, you go test them. And this thing's being very annoying, which is supposed to be saying, let me break out of this and go back and look at, I don't know why it's being so annoying. Anyway, sequence functions. Sequences are lists or vectors. Now, both of them are the same thing, which is to say ordered collections of elements. Lists, we've already described, are a series of locations in memory, each one pointing to the next one. A vector is a block of memory with elements all put together in a single block. The list functions that we've already mentioned are actually sequence functions that they'll work on lists and in vectors. And so let's try this again and see if we get anywhere. Go racing through. Let's see, still a little bit ahead. Where are we? We're at sequences. And it just won't stay there. Extremely annoying. So we're just going to look at the... So sequences are lists and vectors. And lists, there are advantages and disadvantages to using lists and vectors as your data object. Lists are easy to allocate, and it's easy to put new elements in the middle, to append elements to the end or the beginning, but it's very difficult to get to the last element because you have to go through the entire list. There is no way to just jump to the last element. And if you're going through a list and you're, say, at the 10th element and you think to yourself, oh, yeah, I should go back and do something to the 9th element, you can't go from the 10th element back. There are only pointers forward. In order to get to the 9th element, you have to start at the beginning again and start at 1 and go through to 9. And vectors are you allocate basically a vector of a particular size, and that's more or less it. It's not entirely it. You can allocate vectors and say, you know, I might make this vector longer at some later time. but it is extremely difficult to add an element to the beginning of a vector. If you've already assigned the value to the beginning of the vector, then you have to move all the elements in the vector. And let me just show an example of what we mean. So we have a list of employees here, and we have in alphabetical order George, if I could spell, R-G-E, and Harry, and Louis. And then we have Bill shows up, and in fact we can just push Bill onto the front since he's in alphabetical order. Let's make sure I have this available. Yeah. Let's try that again. That's what I meant to do. Ooh, and it's disliking me. Why is it doing that? Let me do this again. And okay, and then push Bill. And but if we had done vector George, and I better quote those, and Louis. Now we have a vector. It's got 3 elements. If a new employee shows up, I've got no space to put him. And even if I had a space to put him, in other words, if I'd done, allowed another space, if I wanted to put Bill in the front, I'd have to move Louis to the 4th place, Harry to the 3rd, George to the 2nd. It would be a great deal of work. In order to splice something into here, we've got L1, and we can push things on the front. It's very easy to splice things in the center. That's the advantage of the list. But the advantage of the vector is we can go through it really quickly. We can access any element if we know what element we want to access immediately without starting at the beginning and running down to the end. The function ELT, similar to aref or svref or char or env for list. Env only works on lists, but ELT works on lists or vectors, including strings, and it just says it's short for element. And unlike env, which takes index list, ELT takes sequence index. And ELT signals an error if you go outside its range, unlike env, which just returns nil. Position returns the position of its first argument in the sequence, which is the specified as the second argument. So position of the character R in microprocessor is 3. M is 0, I is 1, C is 2, R is 3. Now, I earlier tried to use from end with one of the other functions, but it didn't accept it. But position does accept it. So you can say from end T, and then it starts looking from an R at the end. And in fact, it hits it immediately. So it's index 13. And position B only appears once, so it doesn't matter whether from end was T or its default nil. It's going to be 1. Here it is a list. Here's the string. Find searches for an item in a sequence, returns the item found. So you find A in cat, it returns A. You find 1,000 in this list, and it's this element, and it returns it. You try and find 5, and it returns nil. Now, I can hear you thinking, why is it returning the element it found? We knew what that was. It's just the first argument, isn't it? Here it's a character. Here it's the number 1,000. Here it's 5. Why is it returning that value? Isn't there something more useful it could return? But in fact, you can specify what you mean by finding. So the default is the function EQL. It's looking for the number 17 in this list, and it's actually, since it's EQL, it's looking for 17. And 17 isn't there, so you get nil. But you can use the test function to describe what test you are doing. So here we're using the test function less than. The test function must take two elements, the item and the element from the sequence, in this case a list, and so here it's finding the first element of this list, which is bigger than 17. And at this point, you're actually interested in the return value. It's 61. It isn't the same as the item. All of these examples, the return value is the same because we didn't specify a different test function. But you can specify a different test function. Here we define a function is double of two values, and it returns true if the first is double equals the second. And here we're trying to find 17 in this list with the test being is double of, and it finds 34. Excuse me. And here's even a more complicated function. So, and search is a very useful function. It finds a subsequence match. Search ABC in the string, searching for the string ABC in the string 1, 2, 3, 4, 5, 6, returns 3, which is the location of the beginning of the subsequence. The arguments are called seq1 and seq2, so it's the location of the beginning of seq1, in this case the string ABC, in the subsequence. And let me just remind you that Microsoft always converts double quotes into these curly things, and we really mean straight quotes here, but there's nothing you can do when using Microsoft products. So imagine those being straight quotes. It returns nil if there is no match, and the subsequence must not have. So here we have ABC. Even though A, B, and C all appear in the right order, there are other elements between them, so they don't appear as a nested subsequence, and so the value is nil. There's a function subseq, which takes a sequence and then an index, or actually two indexes, a start index and an end index, and returns the sequence starting at the start index and up to but not including the end index. So subsequence, the end index defaults to the end of the list. So subseq with index 1 returns the index 1 element B, in this case, through the end. Subsequence with 1, 2 returns the sequence beginning at the first element, index 1 element, which is B, and ending at the index 2 element, but not including it, so we just get the list B. Now, sequence operations I've described, destructive and non-destructive. Sort is a destructive operation, even though it doesn't have an N at the beginning. And so sort returns a sequence, but it usually destroys its argument. Notice that sort here is increasing order, decreasing order, whatever function you supply there. So let's look at lists again. What is it? Yes. So sort lists, and we're doing less than, and we come out with 1, 2, 2, 3, 3, 4, and the value of lists has been changed. And you think to yourself, the value of lists is actually the result. Isn't that nice? But it needn't be. And Let's see. Set Q, L2, let's just try 5, 4, 3. Sometimes I can get these to work. Sort L2 with less than, is that the way I want to go? No, greater than, yeah, less than. And you see, in this case, it's changed completely. So the thing about destructive functions is that they destroy their arguments. You should not use the value of the argument after you've done that. Normally, you would say set Q. Well, let's get L2 back to what it was. And now you would set the value of L2 to sort L2. Which way are we going? This way. And now, of course, L2 is the thing we want. So removes elements. Delete is the, just can't get this thing to work. Delete is its destructive equivalent. So it destroys the argument, and you, while remove does not destroy its argument. Remove duplicates and delete duplicates, again, destructive, non-destructive, destructive, reverse, and n-reverse. And n-reverse is an example where an n at the beginning says, here is a destructive version. Okay, so we're going to briefly consider streams and files, and then quickly go through path names, and that will be it for today. A stream is an object that's a source of input or a destination for output. Streams include the terminal window, where you're typing to when I move to the Lisp and type to it. Streams to and from a character or a binary file, that is a file on disk. From a window or Windows window or an X window, socket streams, and you can also, so those are the kinds of streams that typically exist. You normally open a stream with the macro with open file, and it takes a variable and then the name of the file you want to open, and then perhaps additional arguments to open, and then you do something. In this case, we're reading lines, and so the read line reads a single line from a stream and returns a string. So this second argument here says don't signal an error when you reach the end of the file. And the third argument says instead of signaling an error, return nil. Since nil is never a string, we know we're at the end when the line equals nil, and this is the return. Remember, this jumps out of the loop. So all we're doing is reading the line and writing lines there. We'll see an example of this in a minute. There are a bunch of standard streams, standard input, standard output are the defaults for where the various reading and printing characters go and correspond to the terminal. The terminal is usually your console, usually has the same value as these two. Trace output is where trace goes. Query is where stream yes or no P goes. There's a whole bunch of predefined streams. Generally, they're all the same thing. You create functions with open. You can specify the direction, input, output, I/O, meaning both input or output, or probe, meaning just tell me whether the file is there, don't actually open it. Element type, the typical elements are character or unsigned byte 8. If does not exist, when you're opening a file, it tells you you should create it. When you're opening a file for output is create. For input, you either get an error or you return nil. If exists, you can supersede, which means replace it. You can overwrite, which means overwrite it, but don't change things until you overwrite them. Error. Append means append to the end of the file. Nil just means return nil, but don't do anything else. This will, if it's successful in opening the file, return a stream object. We'll see examples of this. Once you've opened a stream object, you should close it. If you don't close it, eventually you'll run out of file descriptors, and that number of file descriptors is usually lower than you think, so you run out more quickly. So you have to remember to close streams. The function, the macro with open file does this for you automatically. You don't usually use read because read is for Lisp code, and so the whatever you're reading has to be correct Lisp readable code in order for the function read to work. If you've just got a file of text, you usually read lines and then you parse them. And so read line takes as arguments a stream. EOF error P says, should I signal an error or not when I reach the end of the file? EOF value says, if I don't signal an error, what value should I return? Recursive P, don't worry about, has to do with mostly internal stuff. Read line of the stream. This one will signal an error when the end of the file is reached. Read line with nil nil returns nil when the end of the file is reached. So here's an example, and we're actually going to work out this example in Lisp. And so we have here a function, and it's just got 3 lines. And this is from some mail program. And so this is what the mail header looks like, and it's got a lot of junk in it. And we're going to we're going to open that file, and then we're going to read the lines. So here's what we're going to be doing. We're going to, we've created a block called reading, and inside it is a loop, and where we've created the local variable line, and we're going to read a line of the file, and we have a local variable text, which is initialized to the empty string, and we're going to concatenate all of these lines together so that by the time we're at the end of this loop, and we jump out of it here, return from reading, which is this block here, we could just do return since it's a loop, but it's showing you how to use block here. So at the end of this, the value of the variable text will be all of these lines merged together into one long string. And then we're going to search for the characters from equals less than. And that is the beginning of this from section, which is user2sum.com. And we're going to add 6 to that so that we're actually looking at the very first character, the U there. And then we're going to, starting from that position, in other words, F1, the position of the U, we're going to look for the closing angle bracket. And we're going to get the subsequence from the text and F1 and F2, and then we're going to search for message ID equals. We're going to get the position from there of the closing ones, and we're going to get ID from that. So let's actually open this file, and we'll show you how this works. Stream, and we're going to do open, and it is test.txt, and the direction is input. What do we do? Input. And so now we're just going to evaluate this. And it returned 2 values. That's what these values here say. Return as multiple values, the calculated from and the calculated ID. And the from is user2@sum.com, and the ID is this. we actually go look at the text. Here is the ID, and here is the from. And so this comparatively simple program that we wrote here read this file and parsed it looking for particular markers. And so using the search function, the search looks for a substring within text. So that's just showing you this. It's a rather nice example where you're doing something quite complicated, but not really, just 2 slides of Lisp code here and a couple of the lines of comments. So it's not that difficult to do. In order to figure these things out, well, you just, testing away and you figure out, oh, I have to add 6 and I have to do this. But those things I'm using position and subseq and search, the sequence functions we've already introduced. Now, just quickly, you write lines with write lines, so that's writing them to a stream. Oh, and let me just remind you of something back here in the Lisp. You have to close streams, otherwise you'll run out of. When close returns T, it was a success. You can't read anything more from it. Write string writes a string to a stream, then read char. So we wrote string hello world, now we read a character, gets back H, we write it, and so on. Interpre writes a new line. So when you write an object to a stream, it's the print representation of an object, you read it. If the print representation is readable, and not all Lisp objects have readable print representations, but lists, numbers, strings, symbols, vectors, arrays, and Lisp source code are all print-read compatible, you can read it back. Using the function write, it's rather uncommon. You more commonly use the various print functions, which are illustrated here. And you can also have binary streams. Typically, a binary stream has element type unsigned byte 8, and it writes bytes to it. So you can write binary streams from within Lisp as well as the more common character streams. Okay, the last topic we're going to introduce are path names. Path names are objects which are presumably associated with files, although you can create path names within Lisp that don't actually correspond to an existing file on the machine you're using. Path names are just constructed out of the names that you give for elements. File stream and file functions use path names as arguments. But almost every function which takes a path name as an argument, a path name object as an argument, will work just as well with the string, which is the name string of the path name. So the arguments are called path name designators, and that includes the string naming the path name or the path name object, or actually certain other things that will work. So here to create a path name object, the most common way is to use the function path name, and it takes either a path name object or a string as its argument. If it's a path name object, it just returns it. If it's a string, it creates a path name out of the string and returns it as a path name object. So that's basically what happened here. You can see the return value is hash p, indicating this is a path name, and then the string, which is the name string that it used. So P is a path name, and it has a name, a type, and a version, and various other, and a directory. So the name is the file name, and it parses this string, and I can't quite do that, parses the string and finds the file name, which is typically at the end after the last backslash, but not including the type. So the name of the file is user32, the type is DLL, and the version, well, we don't use versions mostly, so the version is almost always unspecific. The directory, now Lisp represents directories as lists, and it tells you whether the directory is absolute or relative, and the directory is Windows System. Notice it doesn't include the C. That's called the host. I'm sorry, the device. The host is something else. There isn't one in this case, and the device is C. And so it knows that in order to create a name string out of this, it takes a device, follows it with a colon, backslash, then it lists the directories for, separated by backslashes and ending with a backslash, this being Windows. They'd be forward slashes on Unix machines, and actually all these functions accept forward slashes as well instead of backslashes. Takes the file name and the file type. The backslash character is used to escape the next character, so you can have a string that contains double quotes, but you have to indicate that you want the first double quote isn't ending the string by putting a backslash before them. If you actually mean backslash, you have to double them. So C backslash backslash is actually read as C single backslash. And when you have a symbol name in our list, the symbols are all uppercase, but if you put a backslash before a character, it says keep this character exactly as it is. This ends up being the symbol TESTA, and it puts those bars around it to indicate this is has to be handled specially. So there is a function make path name, and you can specify the device, the name, the type, and the directory. And there's a space there shouldn't be. And it will create a path name out of that. As I said, it's much, much more common to create path names with the path name function and the string, unless what you were doing is creating a path name dynamically. In other words, you're computing these values at runtime. You might use make path name. But if you just have a string or a collection of strings, as here, it's much more common just to use the string that names the whole path name and pass it to the path name function. Merge path names is a function which fills in missing fields in the first argument provided by the optional second argument. So merge path name, where we just have the file name ODBC, but the path name we've been using replaces user32 with ODBC, otherwise everything remains the same. There's a variable default path name defaults, which provides the second argument to the merge path names is optional, provides the default for it, and is set to the current directory when you start up. There are a bunch of file operations: rename file, delete file, probe file, file write date. This is what I was trying to remember last week to test whether a file existed or not. And I used file length instead because it had the same effect. But probe file is the correct name. File write date. The directory function gives a list of path names in a directory. The load function loads a list source. A list source that should be or FASL file. Somehow you always notice these mistakes on the day you give rather than when you review these things. So directory C Windows returns a list of directory contents as path names. Let's just try that. Colon, backslash, Windows, backslash. Let's see what it does. And so there's a whole bunch of system, a whole bunch of things. Let's get the whole list just for amusement. I want to start. And it's quite long. So this is just a reminder. Remember earlier I said you don't want to set the top level print length or print level. Notice it only gave me the first 10. If I hadn't, if the print length for the top level print length was nil instead of 5, it would have printed that whole thing out, and maybe I wouldn't have wanted that. I printed it out. I was the one who said to print that out. Anyway, they're all the contents of the directory, the Windows directory on our machine. Okay, well, that's the end. This is the last class of the elementary class. Notes and homework are available. Online help always available. Questions you can always send to training or to support@franz.com. Thank you very much. It's been very enjoyable.